everyone. My name is Sinead Bovell. I am a futurist and strategic foresight advisor, and I am really excited to introduce somebody that would be considered a celebrity to me. So he is a titan of computing. He has shaped the very foundations of modern technology. His work has shaped billions of devices and transformed our digital world. And to not miss any of his accolades, at UC Berkeley, Pardee Emeritus, and a Google Distinguished Engineer. He literally wrote the book on computer architecture, and not just one of them, he wrote 7 of them. His unparalleled contributions have earned him the Nobel Prizes of Computing and Engineering, the Turing Award, and the Draper Prize. Please join me in giving a huge welcome to Dr. David Patterson.
All right.
Thank you.
Thanks. Well, thanks for sticking around to the end. I hope the best is last, so you'll have to get your vote. So this was a controversial title. People in comms weren't thrilled with the how to give AI a bad carbon footprint, but I was a Berkeley professor for 4 decades before I joined Google, and in that time, I gave a series of bad advice talks. My friend and I thought to teach students how to give a talk, we'd tell them how to give a bad talk, and then if you don't want to do that, you do it the other way. So we gave a set of commandments. If you follow, you guarantee to be a bad talk. And then I did one on how to have a bad career, and then how to do a bad research lab, and this is my 4th one that we're debuting today. So the first part is how to do it badly, and then if you don't want to do that, how to avoid doing it badly. And then part of my textbooks that I wrote with John Hennessy, he's my co-author in all those, that we have a fallacy section at the end of every chapter. This sounds right, but it doesn't quite work. So I'll go over some fallacies, and there's a lot of fallacies when we get to talking about carbon footprint. And then Sinead and I will do a little bit of question and answer. Okay, so let's do how to do it badly, how to give it a bad carbon footprint. So the advice would be pick the biggest model, and bigger is better. We know from the scaling laws of OpenAI that the bigger it is, the smarter it is, so go big. Pick an older GPU. The more recent GPUs, like are 1,000 watts when they operate, the older ones could be 1/3 of that, so let's go with an older one. And just pick our local data center. We don't want to have to ship the data all over. We'll just go locally. So let's see how that turns out. So to calculate the emissions, we came up with a mnemonic we call the 4 M's of emissions. And each of these is a factor. When you multiply them together, you get the emissions from AI. So for a model, we're going to pick this open source model, the Llama model from Meta. It's the 405 billion parameter model. So the first thing we're going to count is the number of operations, and in computer terms, number of floating point operations. So that turns out to be that number 3.8 times 10 to the 25th. 10 to the 24th is a septillion. That might be what you learned today. So about 40 septillion floating point operations to train that Llama model. So that's the number of operations. Next, depending on the hardware we pick, it'll turn those operations into energy. So the Volta, which was an older GPU, is the first one with hardware to support AI, hardware acceleration. So it operates at about 300 watts and about 25 teraflops. So that turns out you get an energy for floating point operations out of that. So if you multiply those two together, we get how much energy? But it has to go in a data center. So then the question is, how efficient is the data center? It turns out the industry has standardized on a metric that's called power usage effectiveness. You just take all the energy going into the data center and you divide it by the energy that the computers actually use. So some local data centers will have a power usage effectiveness of 2, which means about only half of the energy goes to equipment and half of it goes for power distributed cooling, so that's pretty inefficient. So when you multiply the model times the machine times what we call mechanization to get an M out of it, that's how much energy you use. And then I think one of the big surprises when we got into this was how variable it is by geography, that the energy intensity or the carbon intensity varies a lot. So to make it bad, we're going to pick West Virginia, because there's a lot of coal mines there, so the public policy is to create energy by burning coal. So if you look at the bottom of the slide, we put those four factors together, and you end up with this number 2.4 times 10 to the fifth kilograms. In this community, the numbers are so big, they use tons. That's British tons, that's 1,000 kilograms. We Americans call it metric tons. So 240,000 metric tons, that's the emissions for training the llama model. That's the bad example. So if we don't want it to be bad, what do? Well, don't do the ones on the right, do the ones on the left. Instead of picking the biggest model, pick the most efficient model. That makes sense. And it turns out you don't want to use an older GPU, even if it uses less energy while it's operating. You want to use the latest GPU or TPU because it's so much faster. So it uses more energy per second, but it takes fewer seconds to run. And then you have to worry about the mechanization, how efficient is data center. Well, the cloud companies have been building giant data centers for 20 years, so they're really good at making them very efficient. So we'll see what the numbers turn out to be. And then, since we're in the cloud, we can train it anywhere. Let's not train it in West Virginia that burns coal for energy. Let's train it someplace else that's much more efficient. Okay, so let's go to our 4Ms again. Instead of the llama model, we're going to use Google's open source model, Gemma 327b. That's about the same quality as the llama model that Google has done. How many floating point operations? It's about 2 septillion floating point operations. That's almost a factor of 20 better than the llama model. So we get a factor of 20 there. Let's go to the machine. Not surprisingly, I'm going to use the latest Google TPU. That's about a factor of 4 better than the old NVIDIA GPU. And I told you when we use the cloud data centers, the power usage effectiveness is really good. It's only about 10% tax. So 90% of all the energy is going for the equipment, and about 10% goes for power distribution and cooling. And then finally, like I said, maps. Given we got to turn all that energy into emissions, let's go to the place that's got the lowest emissions per megawatt hour, and that if we keep it in a place with hydroelectric power, like the Northwest, then we get a much lower number. The last slide, it was 240,000. This slide is 150 tons. And if we kind of go through the numbers, that was that kind of factor of 20 for model times a factor of 4, that's a factor of 80. And then the mechanization is about 2, so that's 160. And maps is about a factor of 10, that's 1,600. And that's very close, right? So by making it, we could make it bad 1,500 times, 1,600 times worse than it was than if we make it good. So you saw the wrong way to do it, and now you can see the right way to do it. Okay, now we're going to move into the fallacies. And when I got started in this a couple of years ago, one of the Googlers gave me a piece of advice going into it. As an engineer, you think kind of everything's science. And she said, energy is physics, so that's still science, but emissions is accounting. So why is it accounting rather than a science? Because you've got this long supply chain, and you got to decide, well, who gets credit for what and who is responsible for what things. So you have to set up an accounting system to be able to keep it fair and make it work for everybody. Okay, so let's go over the fallacies. So the first one was that assumption we made that newer hardware is worse than the older hardware. So I and 4 or 5 friends here at Google just published kind of a breakthrough paper, and it's called a life cycle analysis of AI accelerators. That had never been done before. So life cycle analysis means you take it from cradle to grave. So you get the materials from, mine the materials, and then you put it in semiconductor processing, you get chips out of it, and put chips on boards, you stick them in racks. You have to transport all that to a Google data center and install it. Then it has its operational lifetime, so that's the manufacturing and transportation costs. That's called embodied carbon footprint. Then there's the operational piece over its lifetime, say 6 years. And then at the end, you have to recycle it. So we did the whole cradle to grave approach and did the costs. Now we did this for 5 TPUs. So the 5 TPUs break into 2 sets. What Google Cloud refers to as the versatile TPUs, that's TPU V4i, V5i, and 6E. 6E is the one called the Trillium. And so you can see that's the carbon emissions, smaller is better. So it's about a factor of 3 improvement between those generations, which just took 2 years. That's the overall. If we look at finer detail, the light blue at the bottom, that's the embodied piece, and again, it's about a factor of 3. If we look over at the powerful TPUs, this is the ones that do the training. This is like 4,000 chips in a pod or 8,000 chips in a pod. It's about a factor of 1.2 or 1.3, both overall and then for the embodied. Now I have to get into a little bit the accounting issues here. So why is the tall bar and a dark piece and a light, a medium blue piece there? Well, that's because what's called the Greenhouse Gas Protocol has agreed on how we can account for emissions. The first one at the top is called location-based. That is, just based on what you get from the local utility, how much emissions do you get? But we want people to buy clean energy in addition to what you get from the utility. And so they created a market for that, so that's called market-based. So the light blue bar there is the market-based, and the tall one is location-based. But no matter how you account for it, it's still this dramatic reduction for the versatile TPUs and a significant reduction for the powerful TPUs. So the fallacy was new AI was worse. That was a long explanation about it's actually better. So that was fortunate, right? We didn't know what was going to happen. If it would have been sad for our leadership if we did this study and said, hey, don't use the new TPUs, use the old TPUs, but it turned out to be the best. Basically, they use more emissions, but they're so much faster, they're a better thing to use. Okay, this one's going to take a little longer to do. You see, I've got a movie set facade here, so that's kind of a hint of what the story is going to be. It looks good from the front, but if you go in the back on a movie set, you see it's just empty space and iron. Okay, so I got to tell you an allegorical story to set the stage. So, and then I think it'll be easy to relate. So the allegory is you and your friend Max, you're best friends, you're single, you're young, and you hate to cook, so you eat all your meals out at restaurants, 3 meals a day, 365 days a year. You start getting worried about your health for both of you, but particularly yourself, so think we should start eating more organic food. Well, then you find out there's a society that's trying to promote organic food in restaurants. And so they put little stickers on the menu items that are organic, and when you buy organic meals, you get an organic certificate. And the society, to encourage people to eat more organically, spreads through to restaurants, and they run a leaderboard where the winner at the end of the year gets prizes on that. So you get involved, your friend Max isn't all that excited, and you get, in a year, 365 days, there's about 1,100 meals that you'd eat. You get 800, and you turn it in, and then they announce the prize, and you win. You get accolades, people like you, article newspaper, you feel really good about it. Next year, you want to do it again, so you get up to 900, and you're waiting for the results, and at 900, you come in second place. Somebody has 1,000 meals, even better than you. But the amazing thing is the person with 1,000 meals is Max. You've gone to meals with Max all year. He almost never orders organic. So you confront him, what's going on? So Max says, well, I read the fine print of the rules, and you don't have to turn in the receipts for the meals you eat. You just have to turn in receipts that you buy somewhere. So I looked, and in San Diego, for the cheapest place is San Diego in April for breakfast. So I bought 1,000 breakfasts in San Diego, and then turned those receipts in, those organic receipts, during the year, and that's how I won. Well, then you say to Max, but A, it's not helping your health. You're not eating anything organically. Also, you're not encouraging local restaurants to offer organic food because you're buying in San Diego. And even in San Diego, you're not buying you're only buying breakfast, not the other meals, and you're only doing it in April. So what do you think you're doing? Well, I'm getting all the good press, and I feel good about it, and I like eating the way I am. Okay, so that's the long allegorical story setup. What's the relationship here? So when they set up the greenhouse gas protocol, this accounting system for companies to follow about 20 years ago, as you might expect, when people were buying carbon-free energy, they got certificates. They're called energy attribute certificates. So basically, when you buy clean energy, for every megawatt, you got a certificate. But what some people started doing was kind of like Max. Well, I don't want to buy clean energy from the local one. I'll just buy it in some other part of the country, and I'll just buy it some other part of the year, and then I'll take credit for it. So the difference between those things, when you buy an energy certificate along with the energy, that's called a bundled energy attribute certificate. And when you buy it from anywhere in the country, then you get an unbundled one. And in fact, the rules are any time of the year, anywhere in the same continent. So it doesn't even have to be in the United States. And in Europe, it can be any country in Europe. You can be in France, you can buy it in Poland. Okay, well, like your skepticism about Max benefits of eating organically, academics have studied the benefit, what happens with these unbundled EACs. And what they find is, if companies buy unbundled EACs, that doesn't encourage the local utility to invest in carbon-free energy because you're buying it someplace else. And similarly, you're probably buying it as cheap as possible at a place that already makes it. So even if you're buying it there, it probably doesn't get them to invest a lot more. They've already made the investment. So what they find is the use of the unbundled EACs doesn't really help that much. So there's a market-based economy, and it makes people look good, but it doesn't really help the bottom line. So, okay, now you know what unbundled EACs are and bundled EACs. So how popular are they? That was the next part of my journey. And this article appeared in the Financial Times last year. And here's the top 4 US hyperscaler companies. And what fraction of the carbon-free energy they bought is unbundled? And you can see Amazon's almost 60%, Microsoft's more than half, Facebook is very small, and we're 0, which I was very happy to learn. And now there's the first column is the location-based emissions. That's right out of the tap from the utility. And then if you do market-based emissions, you can see for Microsoft, it looks like 0. They could claim using the unbundled ACs, they have 0 carbon footprint. So that was what the original fallacy that I started this talk with, that basically I read online that these companies are making their operational carbon footprint go to 0, so it's just going to be the manufacturing cost is everything. But no, and the reason is that it's not really as if, it looks good on paper, but it's not really helping the environment all that much. Now, the good news is since about the time we wrote this paper and pointed this out, Microsoft has since announced in the future they're abandoning unbundled EACs. So why did Google not do that? Why did Google not buy unbundled EACs? It's because several years ago they realized this was not really going to help. And so they came up with their own accounting system. And what they wanted people to do, kind of like when you were eating organic food, we wanted that for 24 hours a day, you're using carbon-free energy, 365 days a year, and not you'd buy it in San Diego, you'd buy it where you're using it. So they call their program 24/7 carbon-free energy, and 160 organizations have embraced it so far. There's a United Nations agreement around that. Okay. That's my second fallacy. The third one, which is easier, and you hear this one every day. When I'm listening to the radio NPR on Saturday, I heard this one. The data center AI is a major consumer of global electricity. It's repeated so much, it must be true. So my data source is the International Energy Agency, IEA. It's about an organization of 60 companies that have been doing this together for 50 years, and they're trying to wean these countries off of carbon-based fuels. So they said in 2022 it was about 1.2% of all electricity was data centers, and maybe this year it'll be 1.5%. How does that compare to other things? And in their report, it says that even if data center growth is strong between now and 2030, there's 4 things that'll be much bigger. Just continued economic growth will be much bigger. Electric cars will be much bigger, which I guess you might guess given the popularity of electric cars. But air conditioners are going to be bigger. Just air conditioners all by themselves will be a bigger use of electricity than data centers. And then the last category was high energy manufacturing, like making aluminum or steel. So that's the big picture globally about data centers. What about AI? AI is a small piece of data centers, right? So the assertion that AI is a huge impact on global electricity is far from the truth. But as a caveat, when we talk about a global problem, it's not, but maybe locally it can be. If you put a lot of data centers in one utility, they may not have the power to be able to handle that, and that'd be very stressful for a local area. But as a global issue, it's not a big issue. Now, when I think about air conditioners using more than data centers, it's what are the upsides of air conditioners, and what are they going to contribute societally? Well, AI can make a contribution. So my favorite one is a science result from Google the last couple of years, is contrails. So contrails are the streams, white streams in the sky that follow airplanes. It doesn't happen all the time. It happens when airplanes are in human regions. So aviation represents about 2.5% of worldwide emissions, according to IEA. Contrails, as you saw in the pie chart, is more than 1/3 of emissions is from contrails. Well, if it only occurs when planes fly in certain regions, well, Google can use AI to steer planes as minimally as possible in both an elevation and direction to avoid the human regions. And they did this experiment with American Airlines, and they found they have to increase the fuel that you use a little bit, 0.3%, but it could save, more than half of the contrails. So if you multiply that all out, it could save, if all aviation used this idea, it could save 180 million tons of CO2e. So to put that in perspective, the 4 hyperscalers collectively, using the conservative location-based emissions, was 36 million tons. And if we were to guess what it would be in reality, giving credit for carbon-free energy, it's probably another factor too. So this single innovation from AI, if it was widely deployed, would give a factor of 5 or 10 return on the reduction of carbon emissions for the planet. Okay, and I think with that is my last slide. Oh no, my conclusions. So what are the takeaways? Hopefully, optimizing those 4 M's of machines. We already have data centers that are very efficient in mechanization. Keep building better hardware. People like me do that. AI people building more efficient models. And then, make sure we do it in places that have very clean energy. Companies, beyond using clean energy from the utilities, should try and acquire clean energy on the same 24 hours a day locally, like Google's advocating. But the big picture, I'd say, from my 3 or 4 years looking at this, we have to get the numbers right. Global climate change is a big problem, but if we don't have the numbers right, we won't be working on the right problems. And so recently I wrote a paper about the impact of AI, and I think the thing to keep in mind is this sense. It can be as big a mistake, to ignore the upsides of AI, like the contrail work, as it is to ignore the downsides. And with that, I think we welcome Sinead back on stage, and if you want to read more, there's a bunch of papers. Okay.
Thank you. That was incredible. That was a fascinating presentation. And even just your slide about understanding claims, if they're bundled or unbundled, I think that helps empower all of us when we see these claims to be able to dig down and see what is actually accurate, what's actually helpful. So in your research for this presentation today, what excited and surprised you the most about Google's work in this space?
Yeah, I was thinking about this. I think when I actually did the work, there were 2 surprises. The one was geography matters so much that it's a huge difference as what part of the country you're in. And the second one was, which I was happy that I chose after working at Berkeley to work at Google, is Google has a pretty good job at this. Is like they weren't using unbundled ACs. That was great. They actually, their data centers are very efficient. I think Google is one of the pioneers in trying to come up with this metric of power usage effectiveness and driving it down. And they're pretty, and if you look at, I think they've got 5 data centers that 90% of the energy they use is carbon-free energy. So it was a very pleasant surprise that Google is probably a leader in a carbon footprint in data centers and AI. I think it had to do because maybe the founders of the company were more interested in environmental issues, but it was, if I'd found out that we were the worst, that would have been I would have to rethink where I work.
And earlier this year, there was some buzz about a technological advancement from a company named DeepSeek out of China, that they had brought an AI model to the forefront with low levels, lower resource, commoditized hardware. And then we started to hear about Jevons paradox. So the more energy, or the cheaper something becomes, the more of it we actually end up using. So is Jevons paradox the right framing for the carbon footprint of AI, because people were also kind of throwing that in, or is it something else entirely?
Yeah, so I almost every time I give a talk, somebody brings up Jevons paradox. So Jevons paradox is kind of economics, that if you make something cheaper, well, what economists say, if it's an elastic product, if you make it cheaper, people use more of it. There's some things that aren't elastic, like maybe food production. People don't eat more food if it gets cheaper, but some things, if you make it cheaper, get bigger. But when we talk about reducing the carbon footprint, that's not cheaper, that's making it more efficient. In fact, Google spends extra money to buy carbon-free energy. If they would just use the cheapest energy, which would be dirtier, it gets brought up in that context, but it really doesn't apply. And the DeepSeek people, their breakthrough was training. What they claimed was a breakthrough in training, but when we talk about operational emissions, generally it's probably the inference that's the bigger deal.
Yeah, the inference for sure. What are you doing differently in your personal life as a result of everything you've learned in your research these past couple years?
Yeah, well, there's a couple things. Google Flight, if you search for a trip on Google Flight, it tells you exactly what the carbon emissions are of your flight, and depending where you sit. And pre-COVID, people in China would ask me to come out and give a talk and their first class ticket and all that. And then you go to Google Flight, and I would use up as much energy as the average American for one first class ticket to Beijing. And so I already probably didn't want to go on a trip, but now I certainly fly a lot less. The second one was something we didn't talk about. Is people ask, when I started doing these talks about the data center, they say, well, what about the edge and phones? Well, the big surprise in that one was, when we talked it over, well, the phone actually doesn't draw any energy from the grid. It's the chargers. Well, then we looked at the chargers, and the chargers were awful. Because it's convenient to use wireless chargers. Wireless chargers are much less energy efficient than wired chargers, so we got rid of all of our wireless chargers. And also, there's this thing called vampire power, which means even though the phone's dead, you've left the charger in, and it's drawing power even when you don't use it. And so maybe on average, people have 3 phones, wireless chargers plugged in with no phone on it, using up electricity. So we've become more conscientious about leaving things plugged in and trying to use the most efficient ones. And when we looked at the price, there was no correlation between price and energy efficiency. Once again, fortunately, Google happened to make the most efficient wired charger, which was good in our results, but we couldn't see any relationship. There needs to be like a consumer report. A thing that would make a big difference on electricity and emissions in the world would be people making cell phone chargers more efficient, which is a surprising. It seems like we ought to be able to do that, but there's no incentive to do that as far as I can tell right now.
I mean, I feel like somebody here is probably capable of that as well.
Oh, yeah.
So you're a Turing Award winner. You're an icon in the field, and you've been at this a long time. What advice would you have for some of the developers in this room?
Well, I have two grown sons, and they make fun of me for saying I think I give good advice. But recently, usually for about the last decade, when I give a technical talk at a university, I share some advice of, what I've learned in my life, both technically and personally. And so a year or so ago, I gave a talk at USC, and they said you should write it up. So I have written it down. So you can find my advice. The title is, if you look up Life Lessons from My First Half Century in my career, you can find it. But, I would say, talking about the personal stuff, the family is really important. And, you wouldn't want to sacrifice your family on the altar of success. When you get later in your life, you want to look back, you would really not want to say, well, I've had success, but, I don't have a good relationship with my family. I always made choices for happiness versus wealth. When I grew up in this country, people thought happiness was the same as wealth. There's a lot of unhappy billionaires in this world. So I feel pretty good about it. Like, what's wrong with making choices make you happy? You can't feel bad about that. Finding something you love to do. When I did well in math in high school. There were no computers in my high school. No one ever whispered computers in my ear like in The Graduate or anything like that. So I took math classes to my junior year, and then one was canceled, and a computer class happened to fit in. And when I took it, an intro computer class, and I was hooked. The ideas in your head come alive in the machine. That was it. I had found what I wanted to do. None of my relatives thought, wow, that's a very wise choice. That'll pay off. 10 years later, they thought it was a really good idea. But yeah, so I would find something you love and see if you can get people to pay you for it. And I've got a lot more things like that you can if you find the paper, you can see all the rest of my advice.
So follow what you love, cherish the people who you love, and optimize for happiness.
Do you have more questions? I have a good ending one.
Go for it.
Okay. So one of the other things that I say in terms of like career advice, and maybe personal advice too, I think if you're engineers, I think it's helpful to be optimistic. So many things can go wrong, it's very easy to just give up. Oh, look, we'll never solve these problems. So I think it's better to err on the side of optimism, because in any kind of project, there's hard things to do. So my story about optimism from my life is back when I was a teenager and I was 16, I started going out with this girl and I really liked her, so I asked her to be exclusive. And she said, she thought in her head we're only 16 and she had been with somebody earlier and it's too early for this. So she said to me, well, Dave, you're such a nice guy, I don't know how to say no. So I, as an optimist and a logical person, not a no, sounds like a yes. So I said, great, and hugged her. And she thought, I'll let him down later. I feel sorry for the guy. But we've been married for 57 years and she hasn't let me down yet.
That's a great story.
And now comes so when you say, if you've been married a long time, people say, what's the secret to a long relationship? And I used to say, remember your wedding vows, but nobody remembers their wedding vows. So we have the 9 magic words for a long relationship. It's only 9, and it's 3 sentences, and the first words are I, you, I. And if you say these words, you too can have a long relationship. The first sentence is I was wrong. Second sentence is you were right. The third sentence is I love you. Okay? There's no substitutions. I was wrong, you're right, you're a jerk. Nope, you can't do that. But if you say all 9 magic words, you too can have a long relationship.
I think that's a great place to end.
Yeah.
Thank you. Thank you.